Hi everyone. So in the last video of this electron configuration topic, I want to talk about the fact that uh, when we're talking about the electron configuration of ions, especially ions in the transition metal, the cations, you actually want to be careful with the way you remove electrons from the ions. Okay, so if, for example, I'm talking about just electrons in the main group, let's say, for example, sodium. Now, sodium has a atomic number of 11, has 11 electrons. So if I were to write the electron configuration for the sodium atom, in the ground state will be 1s2, 2s2, 2p6, and 3s1. And for the sodium ion, which is Na+, then it would just be 1s2, 2s2, 2p6, and that's it, right? Because this electron has been removed because it's a plus ion. So in other words, this is fairly straightforward. We know that that's the electron that's going to be removed. Correspondingly, if I were to write something like F versus F minus, F would be 1s2, 2s2, 2p5, right? Because that's the 9 electrons that are in fluorine. And then the fluoride ion, which is F minus, would just be 1s2, 2s2, and 2p6. In other words, you get an additional electron there. Now, this is all fine and good if we're talking about main group elements, which is things like sodium and fluorine. When you're talking about the transition metal, it becomes a little bit more complicated, because what you have to do then is you have to consider the stability of the 3D and the 4s. And as we said before, the 4s is actually a little bit more stable than the 3D when we're talking about just empty orbitals, when we're talking about orbitals that don't have electrons in them. So when you're trying to fill in electrons, when you're trying to put in electrons, the electrons have to go in the 4s orbitals first, because the 4s orbitals is lower in energy. But it turns out that once these orbitals are filled with electrons, the 3D orbitals actually become more stable, and you can see it in this graph right here. This is energy values of 4s and 3D orbitals that are filled with electrons, and you can see that before the transition metal, for the two group 1, group 2a elements, potassium and calcium, the 4s is still more stable even after it's been filled by electrons. Because there's no electrons in the 3D at that point, right? Remember that in the potassium and calcium, you only have electrons in the 4s, you don't have electrons in the 3D. But actually, once you fill in electrons in the 3D, starting from scandium, the 3D orbitals become more stable. And what that means is that if you're thinking about this, your energy diagram, if you go about, if you're writing an energy diagram, for example, okay? In the empty case, right, when the orbital is not filled yet, you have all of these, and then I'm just going to write the 4s and the 3D, right? So this is 4s, and then you're going to have your 3D right here, which is your 5 3D orbital. Okay, so this is your 4s, and then this is your 3D. And this is your empty case, okay? So if it's empty orbital, that's the stability of these orbitals. But when the orbitals are filled, okay, when the orbitals are filled with electrons, you actually have a flip. So in other words, you have 3D, and then you have 4s, okay, 4s and 3D. So when you have electrons in them, so let's say you have a couple of electrons here and a couple of electrons here. This is actually the way the stability works. So in other words, they're flipped, okay? So the difference between a filled and an empty orbital is that the 3D orbital is more stable than the 4s orbital. And this has consequences in the configuration of ions, where you have both of these orbitals. The consequence is the following, as I said here. When you're writing electron configuration for the ions, you have to now remove electrons from the 4s orbital first before you do the 3D, because the 4s orbital is higher in energy. So those electrons will go first before the 3D orbitals, because those electrons now are more stable. So let's take a look at an example. Titanium is a transition metal element, I should say, and it has, the atom itself has this configuration: argon, 4s2, and 3d2. Okay. When I write the titanium plus ion, okay, which is one electron removed, you might have expected that you would write AR 4s2 and 3d1, which is this, but actually that would be wrong, because as I said earlier, the 4s actually then becomes less stable, so you kind of have this at the outside, and 3d is more stable. So when you're writing the electron configuration for the titanium ion +1, it would be AR and 4s1, because you're removing one electron from the 4s orbital, the furthest orbital away, and then the 3d orbital. Okay, so you have to remove this one first. And then if you have titanium 2 plus, it's the same thing. You're going to remove the second electron also from the 4s before you get to the 3d. So in other words, the configuration for titanium 2 plus would be argon and 3d2. You usually, if it's 0, you don't write it, so it would just be argon and 3d2 instead of argon and 4s2, which is what you would have expected. Okay, so both of these are wrong. This is the correct way of writing the electron configuration for these transition state metal ions. I want to mention that this same concept applies for all the subsequent periods. So if you're talking about period 5, where you have these elements here with, you know, something like zirconium, for example, +2, you would do the same exact thing, except now you're comparing the stability of the 5s versus the 4d orbitals, okay? But the same concept applies.